Hi everyone, in today's lesson we're going to talk about defining continuity at a point. But first let's just recall what continuity is. So we said yesterday that a function is continuous if you can trace over the function and not pick up your pencil. Okay, so that is really like not a textbook definition of continuity. The real definition of continuity is this. A function is considered to be continuous at any given x value in a given interval if the limit at that value is equal to the value of the function at that value. So that means if the limit from the left equals the limit from the right, which also equals the value of the function, then we can say it's continuous. Now, sometimes you'll have information about the left limit and the right limit, and sometimes you'll have information about the whole limit. So these two together could be the limit as x approaches c as a whole of f of x. So if that is equal to f of c, then it's also continuous as well. So depending on the information you have, you may use all three pieces or you may use just two pieces. So again, limit from the left has to equal the limit from the right, which has to equal the function value itself. Or the limit as a whole must equal the function value. So let's take a look at example number 1. It says, use the definition of continuity to determine if the piecewise function below is continuous at the given x values. So here is the piecewise function here, and this is the graph of the piecewise function. I've given you the graph for a visual representation, but just note that this graph won't be there when you take exams. So I'm asking at x equals -1. So you can clearly see when x is -1, the graph is not continuous. You have to pick up your pencil, there's a jump. So how would we do this algebraically? Well, we would need to check that this is true, that the limit from the left and the right and the value of the function are the same. So let's do 3 different pieces. Let's do the limit as x approaches c from the left of f of x. But instead of c, we should say -1 of f of x. So we have to look at our piecewise function. And we have some joining functions here at -1 and at 2. So at -1, this function is to be used when I am less than -1. So if you're at a number line, here's -1, here's -2. So all the values that are less than -1 are coming in from the left. So this function up here is my left. So I'm going to plug into that. So -1 squared minus 2 times -1 plus 1. So let's see, what does that come out to? 1 plus 2 is 3, plus 1 is 4. Okay, now let's try the limit as x approaches -1 from the right. So now -1, the values that are to the right of it are 0, 1, and 2, and obviously more, but this is from the right. So clearly bigger than -1 are these values between -1 and 2. So we're going to use this function to evaluate from the right. So we're going to go ahead and plug in into our x plus 2. So -1 plus 2, and that gives me 1. So it's clear that the limit from the left and the limit from the right are not equal. So this can't be true because these first two aren't true. So it's not true that the limit as x approaches -1 as a whole, it's not equal to f of -1. And f of -1, maybe we should have shown that work. F of -1 is the value of the function at -1. So we're just looking where there's an equal sign at -1, which is this function. So the x plus 2 we already did, so that's 1. So f of -1 is 1. And what's the limit as a whole? Limit as x approaches 1 of f of x as a whole technically does not exist. Why? Because the limit from the left is the limit from the right. So it's clear that this limit, dne, does not equal f of -1, which is 1. Okay? Notice it says justify your answer here. That means to show math. Okay, so what I'd actually like you guys to do for homework is to try to prove using the definition of continuity that what's happening at x equals 2. Now you can look at your graph. When x equals 2, it's clearly continuous, right? I don't have to pick up my pencil. So what you're looking for here is that the limit from the left and the right and the value of the function, all three of them are equal, right? And in this one, it was clear. Limit from the left, limit from the right, not equal, so therefore not continuous. So try this one and we'll go over it tomorrow. All right, let's jump to the back and see what kind of questions we have here. So example 2 says, identify any types of discontinuities and where they occur. So honestly, we know that this is a piecewise function, and we know that there's only going to be discontinuities, possible discontinuities, at the values where the functions change. So when I go from the quadratic to the line, or when I go from the line to this next line. So let's just see what's happening at x equals -1. So we're going to check what's happening at this branch. So this is the left side, because they're less than -1. This is bigger than -1. This is the right value. And then this equaling x equals -1, this is the function value. Because there's no like equal sign or underneath. So they're telling you at g of x is 5 when x equals -1. So let's do this. Let's see what happens. The limit as x approaches -1 from the left of f of x, we want to see what's happening there, and we want to see if that's possibly equal to the limit as x approaches -1 from the right of f of x, and we want to see is that possibly equal to f of -1. So the limit from the left, we're going to plug into this function. So we have -1 squared plus 2 times -1 minus 1. So what's that? 1 minus 2 is -1. Minus 1 is -2. Okay, and let's see what happens over here. The limit from the right, which would be this function here, we're going to plug into x minus 1. So -1 minus 1 is -2. So the limit from the left and the limit from the right are equal. Now let's see what happens at the function value. So f of -1. So that means when x is -1, we're literally at 5. So this value is 5. So the first two are equal, but the second is not. So in this case, we have the limit being equal, but we don't have the value of the function. So what's kind of happening? If you kind of want to like look, we have a quadratic. So maybe the quadratic looks something like this, right? And it's approaching x is -1. And it's an open circle because it's not equal. And this one, same thing. It's a line now. What is it happening? It's going straight up. So like this is at x equals -1. We have a quadratic and a line. They meet at the same y value because they're both the same. The limit's the same. Limit from the left, limit from the right. However, at x equals 5, x equals -1, the y value is up here somewhere. It's at 5. This y value down here is at -2, right? If this is your y-axis, right? Here's your -2, and here's your 5. So what type of discontinuity is this? This is a removable. Or in other words, this one is simply a hole. It's not a jump because they reach each other. A jump would be like if one of the branches did something like, say it looked like here's the parabola and then like here's the line. That would be a jump, right? It went from here, jumped up to go here. But this one, since the limit from the left and the right are equal, that means it's just a removable discontinuity. Okay, I'd actually like you guys to try example number 3. Try to see if you can figure out the types of discontinuities that are here. Maybe use the limit definition of continuity. That will help a little bit. And try to see if that helps. And we'll start by going over that one as well tomorrow. But I'd actually like to jump to question number 4. And that'll be the last one that I do. It says, let h be a function defined by the piecewise function. What value of k would make h of x continuous? Justify your answer. So the first function is 2 minus x squared, and the second one is 4x plus k. So we need to find this value that will make it continuous. So we need the definition of continuity. In order for a function to be continuous, the limit as x approaches -2 from the left of h of x must equal the limit as x approaches -2 from the right of h of x, which must also equal h of -2. I chose -2 because that's where these two functions change. We go from this quadratic to this line at x equals -2. Now remember, values that are less than -2 are coming from the left, and values that are greater than -2 are coming from the right. So if I want to evaluate this piecewise function from the left, I'm going to use this one. So everywhere I see an x, I'm going to put in a -2. So we've got 2 minus 4, which is -2. Now the right side of the function, I'm going to use this. So everywhere I see an x, I'm going to put -2. So we're going to leave the k alone. So 4 times -2 plus k. So we can make this -8 plus k. Just for simplicity, I'm going to follow it down. Okay, so now h of -2. That is the function value. Remember, you're looking for the line that's underneath here, right? That's where it's equal to. So here we'd plug into. And we kind of did that on this side. So if you want to do the work again, you can, or if you just want to write the final answer of -2, that's fine. But to find h of -2, you would plug -2 into that quadratic. So 2 minus 4 is -2. So it's clear that in order for these three things to be equal, that we would make an equation, right? This has to equal this, which has to equal this. So you can use any of these two sections and it will work. Like you could put these two together and make an equation and solve, or you could put these two together and make an equation. But bottom line, in order for this thing to be continuous, all three pieces have to equal this -2. So I'm going to just choose these two pieces and put them together, but you absolutely could have used the other two and it really wouldn't have mattered. So we have -2 equals -8 plus k. To solve for k, we add 8, and -2 plus 8 is 6. So the question is, what does the value of k have to be to make this thing continuous? And k would have to be 6. And if you want to check it just to prove yourself, you can. Like change this up here, this k, to be 6. Make it 4x plus 6. So we just have to confirm this side again to make sure it works. So the right side would be 4x plus 6, plug in -2, and we get -8 plus 6 is in fact our -2, which is what we want. Then all three of them are equal, therefore it's continuous. All right, so I know we did a lot today, so feel free to jot down any questions that you might have. Try those two problems, example number 3 from this page and then the one on the previous page, and we will go over them in class tomorrow. All right, have a good night.